Greetings. Welcome to DAU's AI Video Learning Series. In this video, we're going to dive deeper into large language models. We'll take a peek at the ChatBot Arena and see which large language models are top in the leaderboard. We'll talk about some of the cautions for DoD members when using large language models and users in general. We'll learn about how LLMs are trained, what's necessary for the training and for running them in inference, how tool use and multimodal capability has and will help LLMs become more general purpose problem solvers. Then we'll discuss other types of transformer-based AI models besides LLMs like AlphaFold. And we'll peek at what the future might hold for DoD and its involvement with these amazing models. If you have been watching each entry in this series, you're well prepared for this video. If not, to get the most out of it, may I recommend you first watch these 3 videos shown here, starting from left to right. You can click on the thumbnail shown here to jump to that video, or the links will also be repeated in the description below. So let's get to it. So if you haven't had a chance to use large language models yet, you must do that. These models are truly amazing. But a word of caution for DoD members. The Chief Digital and Artificial Intelligence Office, the CDAO, has released interim guidance concerning the use of LLMs for DoD activities. Now you need to get a copy of that guidance and read it. That guidance is CUI, so I can't link to it here, but if you want to use any of these commercial generative AI models for official DoD use, you need to read and heed that guidance. Until then, you can, of course, use these models for your personal use, and I highly recommend you do that. You get access to a good one, and you play around with it and get to learn how to use that. And they're very easy and fun to use. Just communicate with them like they're a person and you'll catch on pretty quick. It probably goes without saying, but don't put anything into the context window. And by the context window, we mean the input window, the prompt window. Don't put anything into these models. Don't type anything in that's not publicly released information, or said another way, don't type anything into the large language model that you wouldn't type into a Google search window. And another word of caution, they can and will hallucinate, i.e. make stuff up. There are tricks to improve the accuracy, and we're going to go over some of those in this video, but always be skeptical of relying on them without first fact-checking the details. So I said get access to a good model. What are some good models? Well, there's this ChatBot Arena that's up on Hugging Face that's managed by a group at Berkeley. This is a great place to go to see how the models are ranking. We'll put the link to this in the references below. So for the purposes of learning how to use these models and getting familiar with them, I would recommend one of these here at the top. GPT-4 Turbo, which is what I'll be using primarily in this video, is an excellent one. That will cost you $20 a month, though, if you want that. The 3.5 version of GPT, I believe, is still free. And then also you see there at the top the Gemini Pro, which is in part of Bard right now. I believe it's going to change its name to just Gemini here very shortly. So while we're here, let's talk about this model down here, Llama 2 70B. Notice that this is Llama Community. So this is an open source model. Meta did the heavy lifting on this and did the pre-training and even fine-tuning. They released a couple versions. They released the base model or the foundation model, which is the pre-training to do that. And then they also released a chatbot version, which is what you see here. And the 70B means it has 70 billion parameters. Now that's a little bit kindergarten level, if you will, when you're talking about something like Gemini Pro or ChatGPT-4 Turbo. I believe ChatGPT-4 has got 1.76 trillion parameters, vice the 70 billion parameters, but nevertheless, it's open source, whereas the GPT-4 Turbo is proprietary. Matter of fact, all these models here at the top are proprietary, which means we can use them through a web interface, but we don't really have access to them. Well, the Llama 2 series of models, and there's a bunch of them. There's a 7 billion one, a 13 billion one, I believe a 36 billion one, and then a 70 billion one. All of those you can download as long as you get, you fill out a little form, you get permission from Meta, and you join the Llama community, and then you can use them. You can't use them for commercial purposes, but they're open to the world. And there's also a technical paper that goes with them that shows you how to use those. So what if we want to make our own large language model? How are these models created anyway? Well, if you're going to make your own, the first thing you're going to need is a lot of training data. Now, traditionally, one scrapes a large portion of the internet. Let's say 10 to 12 terabytes was the case for the Llama 2 70 billion parameter model. And now please keep in mind, this Llama 70B is about 1/10 of what a modern model like a ChatGPT would use to train with. Then you spend millions of dollars to rent thousands of GPUs from a cloud service provider. So GPU stands for Graphics Processor Unit. Now, GPUs were originally designed for processing computer graphics. These versions we'd need would be adapted to train neural networks. And they can do large numbers of computations in parallel, and they're good for adjusting a large number of parameters during the training. Now, when the pre-training's done, you'll have what's commonly referred to as a base model. In the Llama 70B case, Meta did this step for us. Now, the pre-trained Llama 70B model consists of two files. One's parameters, that contains the parameters, the trained parameters, the knob settings like we discussed in Insights to the Fundamentals of a Simple Neural Network video. And then the other file is the source code that you'll need to run the model. Now, one can download both of these. They can run on a more or less regular computer, and you don't need to connect to the cloud, or you don't even need to connect to a network for that matter. You could run these on a machine air-gapped from a network or air-gapped from the cloud. Now, again, just a reminder, if you're going to do this on a DoD machine, you've certainly got to get hold of that CDAO guidance, that interim guidance, and read it and heed it. So it's this pre-training step that forms the base model, which is also known as a foundation model. And this pre-training is what takes the significant time and the money. And so it's done pretty infrequently, maybe once a year. That's why you see the OpenAIs and the Googles coming out with major models not so frequently. Maybe a major model update like GPT-3 to GPT-4 is about a year apart, something like that, because of the significant resources that are involved. Now, without further training, this base model on its own that we get from step one, shown here, the pre-training, it's not very useful all on its own. I mean, I guess if you had an application where you wanted just to predict the next word, then it might be useful for you. But for the most part, you've got to take another step called fine-tuning to make it act and behave like you'd like. Now, it's the fine-tuning in step two that you see here that shapes the model's behavior and makes it act and behave in a manner in which you would desire that base model to act. And this fine-tuning phase uses a much smaller amount of data, but it's a lot higher quality data that shapes the responses and the performance to be the behavior that you would like. Now, let's say we wanted our large language model to be a helpful question and answering chatbot. So the fine-tuning data would consist of thousands of questions, each paired with a corresponding correct answer. And because you have a correct answer paired with a question, it's called labeled data, and you'd use that for supervised training. This would be used to adapt our base model to be a question answering chatbot. The fine-tuning adjusts the behavior. All that knowledge that it gained learning how to predict the next word is still there, but now it can use that knowledge in the manner that it was trained to in step two. Now, this fine-tuning step is still a lot of work, but it's much cheaper and easier than the pre-training phase, so you can do this a lot more often, maybe monthly or even weekly. So an optional step three helps to further align the model to behave and respond in an acceptable manner, and that's called reinforcement learning from human feedback. Now, if one of these large language models ever responds to one of your queries and it gives you two answers to choose from, you're probably training it when you pick one of those answers. And you can kind of think of it as thumbs up, thumbs down training. This training is much less expensive and can be done much more often, even daily if you desire. Now, these three steps are what was used to produce large language models like ChatGPT. The first step, the pre-training, is where the model gets its foundational knowledge. Now, the second and third step, those are used for alignment, to align that model so that it behaves in a manner in which we desire. So this file that results from the pre-training, you can kind of think of it as like a zip file, but it's not an exact representation. It's the training data captured in the parameters, but it's kind of like when we remember things. You know, it's much better than me anyway, with it, as far as its memory goes, but it's not an exact copy. It's just sort of the gist of that training data, representation that gets stored in the parameter values. Now, these parameter values, they're arrived at by going through the training data word by word, teaching the model to predict each new word. Now, what you see here is a representation of OpenAI's GPT model as it makes its way through predicting the nursery rhyme Jack and Jill went up the hill. Now, this demo shows the model that's in inference, so it's an already trained model as it's going around. Now, if this was a demo of the training phase, and specifically the pre-training phase, you would expect some bad guesses along the way. So if when a model guesses the wrong word, let's say, Jack and Jill, and instead of went up the hill, it said Jack and Jill eloped. Okay, so the model's guess is compared to the next word, and a loss function is generated. And that loss function is a representation of the error between the guessed word and the actual word that it should have been. So then an algorithm called a backpropagation algorithm uses that loss function to go backwards down through the model, adjusting all those parameters so that next time there's a better guess. And you can think of adjusting the parameters like adjusting the knobs or tuning a radio. And if you watch the Insights to the Fundamentals of a Simple Neural Network, you'll see that explained there. But in the case of Llama 2 example, we're talking about 70 billion knobs that you have to tune with every single bad guess. Okay, so that's a lot of compute power to adjust all those parameters. So the process is repeated through the entire data set, and that's called an epoch. And usually it takes many epochs to get through to get the loss value down to an acceptable value. So if you ever train one of these, you'll see the error value come down to a small value, and then hopefully it stays there, and that's called converging. Now you may hear some people talk poorly about large language models, calling them glorified autofill machines. Now Yann LeCun is one of these. Yann LeCun has been adamant about his dissatisfaction with large language models. He's one of the godfathers of artificial intelligence. Yann LeCun, along with two of his colleagues, received the 2018 Turing Award, often referred to as the Nobel Prize of Computing. They received this for their work on deep learning. And for this, those three are usually referred to as the godfathers of artificial intelligence. Now, Yann has given many presentations with slides like the one you see here that indicate these models don't really understand what they're doing. And Geoffrey Hinton, on the other hand, he's another of the AI godfathers. Now, he has a different outlook from Yann. He believes that chatbots like Gemini and GPT-4, they really do understand what they're saying. Now, not in a sentient way, of course, but in a real understanding of the language. And he believes there's an urgent need for the research community to come together on this matter of understanding, as he thinks it might hinder the progress moving forward. Now, in another video referenced at the bottom of the screen here, Geoffrey Hinton said, the idea is that it's just sort of predicting the next word and using statistics. There's a sense in which that's true, but it's not the sense of statistics that most people understand. From the data, it figures out how to extract the meaning of the sentence, and it uses the meaning of the sentence to predict the next word. It really does understand, and that is shocking. So the debate is on as to whether these large language models really understand or not, and I'll leave it to you to ponder the differing perspectives of these two godfathers of AI. It would be great to hear your thoughts on this in the comments. Are these models really understanding? Do we need better definition of maybe what understanding is? Let me know in the comments what you think. One thing I will add, though, is there's something kind of magical, or to say the least empirical, about these models' knowledge. We completely understand the architecture of these models. We understand every single calculation that's involved in the learning algorithm, but we don't really know why they work. We don't understand how they can learn like they learn, and there's really no theory backing this up. The models have, for the most part, largely been trial and error. And their performance, especially the recent models like those at the top of the leaderboard we showed earlier, their performance is truly amazing. So from teaching the model to predict the next word, we get this lossy zip-like file, not an exact copy of the training data. Okay, I got that. But also it's kind of strange and empirical. For example, in the AI models, they sometimes only seem to know things in one direction. The phenomenon that this paper here made famous was, they dubbed it the reversal curse. And said another way, these models only seem to know things in one direction. They seem to lack deductive reasoning. And I say it sometimes because GPT-4 didn't show this behavior when I tested it. In the case this paper made famous, the model was asked, who was Tom Cruise's mother? To which it correctly replied, Mary Lee Pfeiffer. But when they asked it who was Mary Lee Pfeiffer's son, it claimed it didn't know. So of course I had to go try this, and this exchange you see right here is with me and ChatGPT 3.5. Luckily I saved this thread, because when I went back to try to duplicate it on ChatGPT 3.5 again, it knew that Tom Cruise was Mary Lee Pfeiffer's son. So I think the takeaway is not so much the reversal curse here, but I think the takeaway is these models don't really think like humans, and after you use them for a while, you're going to be tempted to think they do. But they have a strangeness about them that you should always be a little bit leery when you're using them. Especially keep this in mind when you're considering that using them for some official DoD application. And remember, again, the CDAO interim guidance, please go get a copy of that and read it. So whether you're new to using large language models or a seasoned novice, you should always stay cognizant of the potential for hallucinations. Hallucinations are instances where the model confidently generates inaccurate results that are not justified by its training data. So these can range from minor inaccuracies to complete fabrications. And they can sound so conventionally confident and correct that you're going to be tempted to just believe them. Now, while the newest and best models have greatly improved in this area, all models are still susceptible to hallucinations. Hallucinations usually result when the training data didn't contain the information needed or was of poor quality. Current models don't really understand like humans do. There's that U word again for understanding, but nevertheless, these models don't understand the same way that humans do. At their core, they are recognizing and learning patterns in the data, and they will predict the next word. So whether or not there's sufficient data or not, they're going to go ahead and keep chugging along, plugging and chugging, predicting the next word, whether they have high confidence or not. So in the cases where the probabilities are low and many different words could possibly be selected, there's a really good chance they're going to take that wrong pathway through the multi-dimensional language space. See the video How AI Learns to Talk to understand that multi-dimensional language space. In essence, one bad guess will lead to another bad guess and so on and so forth, resulting in a hallucination. Now, that all being said, these models are getting much better all the time, and they have at least some capacity now to self-check. And there's ongoing research in this area, and the models will continue to improve, I'm sure. But there are also things that users can do to help minimize those hallucinations. Now, it's been found that asking the model to role play can actually reduce the hallucinations. So if you tell it what you actually expect of it, so for example, telling it that it's an expert and it should provide factual, concise, and accurate response, that's actually been found to improve the model's accuracy. If you ask clear, descriptive, succinct questions, and if you limit the model's response, you tell it to keep its answers brief or say less than 100 words. Also, you can supplement its training data by actually inserting a PDF file, which we'll talk a little bit more about later. But all of these practices can improve accuracy and decrease hallucinations. So chain of thought prompting can also improve the accuracy of responses. It's a technique where you provide the language model with a prompt that encourages it to think aloud or step through a problem-solving process before it gives you the answer. It's designed to mimic the way humans think when we try to solve problems by breaking them down into smaller parts. This particular technique is very useful with math problems, logic reasoning tasks, and anything that requires understanding and integrating multiple pieces of a problem-solving method together. So if you simply put in the model in the prompt, think step by step and show your work along the way, that'll improve your accuracy. Now, one other thing, let me show you real quick. So here's my ChatGPT 4, and if I go down to my settings, and if I look at my custom instructions, and ChatGPT 4 will let you put in custom instructions so you don't have to type the same thing in the prompt every time, like think step by step. So here's what I have in mind. It would like you to, be casual and friendly, blah, 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 and all that stuff. So please provide a confidence level with your answers. So I'm asking it to tell me how confident it is. Now, if you speculate or predict something, please let me know. Please keep your answers as short as possible and concise as possible. Think step by step and share your work along the way. That's what we were just talking about. You have a high IQ. Please strive to answer accurately as possible and share your reasoning as you think through problems step by step. Lastly, if you are able, please provide a URL. So those instructions help a lot. Sometimes when I'm doing a problem that I know is going to require chain of thought reasoning, I will go ahead and remind it again, and please work through this step by step. Every indication with regards to these large language models is that bigger is going to continue to be better. The model performance is a smooth function of two parameters. One, the number of parameters, the number of weights in the model, and two, the amount of data that it's trained on. And this is almost a guaranteed path to better performance. And you can see here from this graph from this GPT-4 technical report that GPT-4 is the green above the blue, which was GPT-3, and this is their performance on standardized test scores. Now, GPT-4 had 1.76 trillion parameters, and GPT-3 had 175 billion parameters, so that gives you some idea of increased performance. Scaling not only increases the accuracy of predicting the next word, new abilities not previously seen have suddenly emerged with the increased model size. For example, generic arithmetic, multiple task natural language understanding the meaning of words in context. All these are emergent properties that have all indicated in a lot of different models at about the same parameter value. And additional abilities may emerge still in models of the future. Of course, it's not just size that matters. Algorithm improvements and data quality those are big needle movers also. Now, it's beyond the scope of this course to dive into specifics on this, but this Mistral 7B model is very encouraging. It's a 7 billion parameter model, and if you noticed on the leaderboard we saw earlier, it was not too far down below the proprietary big models, and it's starting to climb up on the rankings. It's also an open source model. You need an Apache license through the company to use it, but you could use it for commercial properties. And it's got pretty good inference, so it doesn't take as long or as much compute power to run an inference. That's one example of good data and good algorithms can also increase the performance. So one of the major abilities that were seen with early large language models was the ability for these models to still learn even though the parameters are frozen. So you can think of two layers of learning. There's that core learning that we talked about above with step 1, 2, and 3. The pre-training, the fine-tuning, the reinforcement learning from human feedback. That's step 1 of this learning. During that phase, you're adjusting the parameters. So if the model makes a guess and it gets it wrong, then the back propagation algorithm adjusts all the parameters so that it makes a better guess next time. Now that's what we usually traditionally think of when we're talking about machine learning. But now we have a new kind of learning that we've seen with these models as we've made them bigger and scaled them up, and that's called in-context learning. So what do I mean by in-context? I mean it can learn in the prompt window. So you type something in, you give it a few examples, it can learn from those examples without the weights being changed at all. So with frozen weights, it can still learn in that in-context window. It can learn during inference, which is amazing. To some of us that have been using this for a long time, this seems like old hat, but this is huge. And when this first happened with GPT-3 and that GPT-3 paper that on the screen came out, it was pretty shocking and opened up some big possibilities. Now here's a page from that GPT-3 report. They taught the model in the context window, all the weights are frozen, they taught the model a new word, they made it up, called Baringo. And that was a car with a really fast acceleration. And later in the text they asked, hey, use that word Baringo in a sentence. And the model replied, in our garage we have a Baringo that my father drives to work every day, which is it's an amazing demonstration that the model has a fundamental understanding of language comprehension and really learn that new word. So this in-context learning is huge. It transforms AI into a dynamic tool that will forevermore change the way we interface with machines. This ability to learn in context allows large language models like Voyager here in this paper, they demonstrated to open up really new frontiers with artificial intelligence and showing abilities far beyond that of simple conversations. Now this Voyager was a large language model that was acting as an autonomous agent. It learned, adapted, and solved complex problems in this virtual environment of Minecraft. So it showed that these LLMs can be put into an environment and they can do much more than just be chatbots. I mean, they're tool users, they're explorers, they're innovators, they're problem-solving decision makers. I mean, this Voyager paper really showed that LLMs have incredible strategic importance in the future, and this shows us for DoD that there's great strategic importance here for LLMs also. We should think of them a lot more as just chatbots. They can help us out in things from simulation and training to autonomous decision making. So in the context of artificial intelligence and machine learning, we can think of an agent like Voyager as an entity that can perceive and act on its environment. So AutoGen is a framework that Microsoft came up with that simplifies the integration and management of conversations between these large language model agents. It makes it so much easier to develop complex multi-agent systems. Now you can kind of think of maybe swarms of Voyagers running around talking to each other, but Voyagers not in Minecraft world, but in the real world that are actually running around communicating with each other, talking with each other. With GPTs, OpenAI has given everyone the ability to tailor large language models to their specific purposes. Now you can set general instructions for these customized GPTs. You can add to their knowledge base by uploading files like PDF files, so they have in-context learning, that they can learn new information that was not in their knowledge base. You can also have them use plugins like math packages, so they know how to do math better. And they can also do API calls, application program interface calls, so they can call other, like AutoGen we just talked about, they can call other large language models, or they can call other programs, or they can go out and search the web, an API call to Google or whatever to go out and search the web, so they can supplement their knowledge that way. All these various GPTs that you see Sam Altman standing in front of here, think of this kind of as an app store on an iPhone. Well, this is a GPT store in the OpenAI environment. All right, so LLMs, large language models, are already tool users. We're talking about this for the future. They're going to be tool users and problem solvers, but we're already seeing glimpses and very good glimpses of this already. Like we just talked about, you can already augment their knowledge with PDFs and internet searches, and they can use existing infrastructure like Python code. They can go out and grab a calculator if they need it. They can hear and speak, so they can actually use speech synthesizers and generate speech. They can see and generate images, and you can have the custom GPTs like we just talked about, and they can also communicate with other large language models and other applications with APIs. Now, what I'm showing you here is an example I did when I asked it. I said, can you go ahead and plot me a graph? And I gave it the equations. And here's an example of a hallucination. It confidently plotted these two lines, and he told me that the intersection of these two, I hadn't asked for the intersection, but it told me the intersection was 2 and 7. And I said, that's interesting. So I went back and said, hey, could you revisit your calculations above, and could you think step by step and redo this? And it went back and thought step by step and came back and said, oops, I'm sorry, I made a mistake. Went ahead and replotted this and showed me the new graph. And it did this in Python. And I could click right here and it would open up basically a Jupyter Notebook-like window where it wrote all the Python code. And so it has the ability to write Python code and make graphs like this right at its fingertips. And I copied, of course, I had to copy that code. I see it run right here, but I had to copy that code and drop it in a Jupyter Notebook and watch it run. And of course, it did run flawlessly. And it's a really good code writer too, by the way. But it has all these abilities already, all these tool using abilities already. So you may have seen this video. If you have access to ChatGPT-4 Turbo on an iOS device, then you can actually talk with ChatGPT just like they were a person sitting right next to you. This AI on AI in the DoD was an interview I did with ChatGPT where we just talk with each other. And it's really an amazing, kind of magical experience if you haven't had a chance to do this yet. Now, so far we've talked about transformer architectures that have been trained on large quantities of text, which of course we call large language models. Now, these are also known as natural language processors. But these transformer architectures are truly amazing, and there's absolutely no reason that they just have to be limited to text. Like, for instance, AlphaFold here. AlphaFold learned the language of protein folding. Now, this was something scientists had struggled with for years. That people got their PhDs learning to fold a single protein. And AlphaFold now can do this with relative ease. And VITs, vision transformers, they can see images. There are transformers that can recognize speech now, generate music and images too. All these images on this slide here were generated by DALL-E 3, which is a transformer architecture to generate images from a prompt. And those transformer architectures can learn multiple modalities at once, kind of like we do. We don't just learn text and then later learn vision and later sounds and then speech. We learn everything together. We usually refer to these type of transformers that learn everything together as multimodal large language models. We still put the large language model in there, but we call them multimodal large language models. Now, most of these multimodal models that are in use today are really late fusion. So you see this little GIF here that's integrating these text and image and sound and video together. Most of the integration today happens either midway through or toward the end. So they'll learn text by themselves and then add on something else. But there is ongoing research for early fusion, so they learn more like we do with all of them at the very beginning. And there are some models that can do a couple modalities at once now. So one note here for DoD members, there's absolutely no reason that these images have to be limited to sound and video and text. I mean, these could just as easy be RF imagery or IR imagery or sonar or LiDAR clouds or whatever the case may be, and those could learn right along with the other modalities in there. Now, there are some models out here, some mid-fusion to late fusion models. Gemini, we don't really know the details on Gemini, but it seems to have all the behaviors of a mid, even almost early fusion model where it's maybe learning earlier. Some of these demos that they did were just truly amazing. Now, they caught a lot of heat for editing some of these, but this is the way a multimodal model acts. There's also a Chinese model out called VeryToy. It just came out like last week. This paper came out. Now, it's a pretty small model. That's 1.8 billion parameters. That was a spin-off from a bigger model called Vary, V-A-R-Y, which was another Chinese model. But these are multimodal models, and you can see in this little graphic here, this little demo, somebody drew a happy face on the fire hydrant, and the model recognized the picture and described exactly what it saw. So pretty amazing, a lot of potential here. In Andre Karpathy's video, Intro to Large Language Models, he states he doesn't think it's right to think of LLMs as chatbots, but instead you should think of them as the core of a future operating system. Now, this diagram from his video, this looks similar to a computer of today, where a large language model would be in the middle, would be the CPU. And the context window would be like the random access memory. And the large language model would be managing that precious resource, shuffling items in and out of that context window as it tried to solve the task at hand. And we've already talked about a lot of parts of this that have already come to be today, with large language models acting as tool users, internet browsers, and the like. Now, if this video of mine piqued your interest here, you may really want to take the hour to watch Andre Karpathy's 1 hour video. He's really good, and he's a really great teacher, and some good information in there. So changing gears just a bit here, digital engineering, also known as model-based systems engineering, is being used more and more in defense acquisition. Now, the Air Force actually mandated it under Dr. Roper's watch. Now, if you don't know what model-based systems engineering is, or even if you do, a really good video for you to watch is this one right here that's referenced below. I'll put this also in the description below. But it's kind of a fun introduction to model-based systems engineering. And it's beyond the scope of this course to dive in very deep here, but the idea is you develop better and better versions of a system in virtual space and modeling and simulation. And then you learn from testing those virtual models and you improve them in the virtual space. And then occasionally you go out and build a real one and try it out, make sure it works the way the model says it works and validate the model. But then you iterate like that, so you can iterate much quicker on designs. Now, this is commonplace today. Formula One racing, it's done all the time in Formula One racing. They've gone through so many iterations by the end of the season that the car that they start the season with wouldn't even qualify for the last race of that season. So that's how fast they're improving the car iterations. And we're already doing this in the Air Force. The T7 is a version of this. They call it e-create before you aviate. So create it in the virtual world and then go out and actually do it in the physical world. So, this isn't really new, at least the model-based systems engineering is not really new. This was a program I was on back 2 decades ago. This is AIM-9X. And AIM-9X, we acquired a modeling and simulation suite, a pretty high fidelity modeling and simulation suite that modeled not only the missile, but the seeker and also the environment that it flew out in. So it was a 6 degree of freedom model that really represented the physical world. And we could get all the data we needed to help develop that seeker and get a good tracking just by shooting simulated shots. And we would shoot a Monte Carlo of shots before we ever went out and shot a real missile. And it would give us a statistical probability, what we used to call a pin cushion. And lo and behold, more times, almost every time, that missile went right through the middle of that pin cushion, right where it said it was going to go. And this little video you see here is actual seeker head, or at least on the right is actual seeker head. What's on the left is a simulated flyout. And the reason I bring that up here is because these models and simulation give you everything that you need, or everything the AI needs to learn. AI thrives on data. And these models and sims generate tons of data, and they can generate all of the data that the AI could possibly need to learn how to even to fly the missile. Or in this case right here, New Zealand has commissioned AI, an artificial intelligent bot, to actually sail their yacht. And what they had is they had model-based systems engineering, and they were iterating on the designs of their yacht so they could get better and better yachts. But the sailors didn't have time to go down there and sail every single iteration of this new design on the simulator. So they got McKinsey & Company to design an artificial intelligent bot to go ahead and sail the yacht for them. They were a little skeptical this would work, but it did work. And it started doing things the sailors were thinking it was kind of odd. It was tacking funny, it was doing things, but then it started beating the sailors, and the sailors were like, oh. So they started imitating the bot and learning from the bot. And the competitive nature, they competed with the bot, got to be better and better in sailors. And if you know who won the last America's Cup match, it was New Zealand. And certainly the AI had something to do with them winning, since they've incorporated AI. One thing we haven't talked about yet is the vulnerabilities of these large language models. Now, with any new system, there's going to be hackers that try to hack into it. Certainly the case here. There's jailbreaks and all kinds of other things that are going on. But we're going to save this for another video because this one's getting kind of long. I think we'll partner with our cyber department and come up with some of the vulnerabilities and the cat and mouse game that happens between the countermeasures and the countermeasures to counter those for the large language models. If you'd like to take any of DAU's courses, then please click on the link here, or the link will be down in the description of the video, and it'll take you to a playlist of courses that DAU offers that you can take on AI. And thanks for watching. Please check out all the other videos in our series. And if you like that, please leave a thumbs up and get active in the comments. Let me know what you'd like to see, what you're getting out of this, or constructive criticism also works too. I'd love to hear your comments and your suggestions. All right, well, thank you very much.